Look up at the night sky. On a clear, dark night, you might see a faint, glowing band. This band stretches across the entire celestial sphere. This beautiful, hazy strip of light is the Milky Way. It is our home galaxy, our grand cosmic neighborhood. We are not just looking at it, we are actually inside it. Imagine standing within a bustling city made of stars. The Milky Way is that city, and Earth is just one tiny part of it. This perspective changes how we see our place in the universe. It is truly a humbling thought, isn't it? What exactly is a galaxy, you might ask? A galaxy is an enormous collection of stars, gas, and dust. It also contains something mysterious called dark matter. All these components are bound together by gravity. Our Milky Way is just one of billions, perhaps even trillions of galaxies in the observable universe. Each galaxy is like an island universe floating in the vast ocean of space. Some galaxies are small with only a few million stars. Others are giants containing trillions of stars. Our Milky Way is a large, majestic spiral galaxy, a truly spectacular place to call home. The name Milky Way comes from ancient times. The Greeks called it Galaxias Kyklos, meaning Milky Circle. The Romans called it Via Lactea, which also means Milky Road. Many cultures around the world have their own myths and legends about this celestial river of light. They saw it as a path for spirits, a divine river, or the spilled milk of a goddess. These ancient stories show how humans have always been fascinated by the stars. They looked up and wondered about their place beneath this starry expanse, just as we do today. Why is it so important for us to study our own galaxy, the Milky Way? Well, it is our immediate cosmic environment. Understanding the Milky Way helps us understand how galaxies form and evolve. It tells us about the life cycle of stars and the formation of planets. By studying our galaxy, we learn about the conditions that might be necessary for life to arise. It provides a crucial context for our search for life beyond Earth. The Milky Way is our cosmic laboratory, offering endless opportunities for discovery and wonder. It's the first step to understanding the entire universe. Let's talk about the sheer size of the Milky Way. It is almost unimaginably vast. Our galaxy is about 100,000 light-years across. A light-year is the distance light travels in 1 year, which is nearly 6 trillion miles. So light takes 100,000 years to travel from one side of our galaxy to the other. Think about that for a moment. The Milky Way contains hundreds of billions of stars. Some estimates go as high as 400 billion stars. Our sun is just one of these countless stars, a rather average one at that. Grasping these numbers can be difficult, but it highlights the grand scale of our galactic home. What about the shape of the Milky Way? It is a barred spiral galaxy. This means it has a central bar-shaped structure made of stars. 2 major spiral arms and several minor arms extend outwards from the ends of this bar. These arms are regions where stars are actively forming. They are filled with bright young stars, gas, and dust. Our solar system, including Earth, is located in one of these spiral arms. We are in the Orion arm, about 2/3 of the way out from the galactic center. We are not in the crowded downtown, but more in a comfortable cosmic suburb. The Milky Way has several distinct components. There is the central bulge, a tightly packed region of mostly older stars surrounding the galactic center. Then there is the disk, which contains the spiral arms, young stars, gas, and dust. This disk is relatively thin, only about 1,000 light-years thick. Surrounding the disk and bulge is the halo. The halo is a much larger, spherical region. It contains very old stars and many globular clusters, which are dense collections of ancient stars. The halo also seems to be dominated by mysterious dark matter. At the very heart of our Milky Way lies a supermassive black hole. This cosmic monster is called Sagittarius A*, pronounced Sagittarius A star. Scientists detected it by observing the rapid orbits of stars near the galactic center. These stars are moving so fast that only an object with immense gravity could hold them. Sagittarius A** has a mass about 4 million times that of our Sun. While that sounds enormous, it is relatively calm compared to black holes in some other galaxies. Its presence shapes the dynamics of the inner galaxy, a powerful engine at our cosmic core. The Milky Way is teeming with a stunning variety of stars. They come in many different sizes, colors, temperatures, and ages. We have small, cool red dwarf stars, which are the most common type. They burn their fuel very slowly and can live for trillions of years. Then there are massive hot blue giant stars. These stars live fast and die young, often ending their lives in spectacular supernova explosions. Our Sun is a medium-sized yellow dwarf star, currently in its middle age. Each star is a sun to its own potential system, a beacon in the galactic night. Beyond individual stars, our galaxy hosts magnificent structures called nebulae. Nebulae are vast clouds of gas and dust. Some nebulae are stellar nurseries, like the famous Orion Nebula. In these regions, gravity pulls gas and dust together to form new stars and planetary systems. Other nebulae are the remnants of dying stars. For example, planetary nebulae are the glowing shells of gas ejected by sun-like stars in their final stages. Supernova remnants are the expanding clouds of debris from exploded massive stars. These nebulae enrich the galaxy with heavier elements, crucial for forming planets and life. Of course, where there are stars, there are often planets. Our own solar system, with its 8 diverse planets, is just one example. For a long time, we could only wonder if other stars had planets too. Now we know they do. Astronomers have discovered thousands of planets orbiting other stars within the Milky Way. These are called exoplanets. It seems that planetary systems are very common. Most stars in our galaxy likely host at least one planet. This means there could be billions, perhaps even trillions of planets in the Milky Way alone. Imagine the variety of worlds out there. A significant yet unseen component of our galaxy is dark matter. We cannot see it directly because it does not emit, absorb, or reflect light. However, we know it exists because of its gravitational effects on visible matter. Dark matter makes up about 85% of the total matter in the universe and a large portion of our galaxy's mass. It forms a vast halo around the Milky Way, influencing how stars and gas move. Without dark matter, our galaxy would fly apart. The nature of dark matter is one of the biggest mysteries in modern astrophysics. Solving it will revolutionize our understanding of the cosmos. So what exactly are exoplanets? The term exoplanet is short for extrasolar planet. These are planets that orbit stars other than our Sun. For centuries, philosophers and scientists speculated about their existence. Were there other Earths out there? Could other stars have families of planets like our own solar system? The first confirmed discoveries of exoplanets in the 1990s transformed this speculation into an exciting field of scientific research. Finding these distant worlds is a testament to human ingenuity and our relentless curiosity about the universe. Each new discovery adds another piece to the cosmic puzzle. The number of potential exoplanets in our galaxy is truly staggering. Think about it. If the Milky Way has hundreds of billions of stars and most of them have planets, the total count of exoplanets must be enormous. Current estimates suggest there could be more planets than stars in our galaxy. Many stars likely have multiple planets forming diverse planetary systems. This implies that billions, perhaps even trillions of worlds are scattered throughout the Milky Way. Some might be rocky like Earth, others giant gas balls like Jupiter, and many could be entirely new types of planets we have yet to imagine. The exoplanets discovered so far show a remarkable diversity. We have found hot Jupiters, which are gas giants orbiting very close to their stars, much closer than Mercury is to our Sun. There are super-Earths, rocky planets larger than Earth but smaller than Neptune. We have also found mini-Neptunes, which are smaller versions of our ice giants. Some exoplanets orbit 2 stars, like Tatooine from Star Wars. Others are rogue planets, drifting through space without a host star. This variety challenges our old ideas about how planetary systems form and evolve, showing us nature's boundless creativity. A key concept in the search for life on exoplanets is the habitable zone. This is also sometimes called the Goldilocks zone. It is the region around a star where conditions might be just right for liquid water to exist on a planet's surface. Not too hot, not too cold, but just right. Liquid water is considered essential for life as we know it. So, finding rocky exoplanets within the habitable zones of their stars is a primary goal for astronomers. It does not guarantee life, but it certainly makes a planet a more promising candidate for further investigation. Section 5. Techniques of discovery, how we find distant planets. Discovering exoplanets is incredibly challenging. These planets are extremely far away. They are also very small and dim compared to the bright stars they orbit. Trying to see an exoplanet directly is like trying to spot a firefly next to a powerful searchlight from miles away. While direct imaging has been successful for a few large planets far from their stars, most exoplanets are found using indirect methods. These clever techniques rely on observing the effects a planet has on its host star. It requires patience and very precise instruments. One of the most successful methods for finding exoplanets is the transit method. Imagine a planet passing in front of its star, as seen from Earth. When this happens, the planet blocks a tiny fraction of the star's light, causing a slight, temporary dimming. Astronomers can detect this dimming if they monitor the star's brightness very carefully over time. NASA's Kepler Space Telescope used this method to discover thousands of exoplanets. The amount of dimming tells us the planet's size, and how often it occurs tells us its orbital period. It's like watching for tiny eclipses far, far away. Another powerful technique is the radial velocity method, also known as the Doppler wobble method. As a planet orbits a star, its gravity tugs on the star, causing the star to wobble slightly. This wobble is tiny, but it can be detected by observing changes in the star's light. As the star moves towards us, its light waves are compressed, shifting towards the blue end of the spectrum. As it moves away, its light waves are stretched, shifting towards the red end. This is the Doppler effect. By measuring these shifts, astronomers can infer the presence of an orbiting planet and estimate its mass. There are other methods too, each with its own advantages. Gravitational microlensing occurs when a star with a planet passes in front of a more distant star. The gravity of the foreground star and its planet can bend and magnify the light of the background star, revealing the planet. Astrometry involves precisely measuring a star's position in the sky to detect the wobble caused by an orbiting planet. Future telescopes like the James Webb Space Telescope and the Roman Space Telescope will use advanced techniques to find even more exoplanets and even study their atmospheres, bringing us closer to understanding these distant worlds. Section 6. The burning question: is there life out there? The question of whether we are alone in the universe is one of the most profound questions humanity can ask. It has been contemplated by philosophers, scientists, and storytellers for centuries. What would it mean for us if we found life beyond Earth? If we found simple microbial life, it would tell us that life is not unique to our planet. If we found intelligent life, it would revolutionize our understanding of our place in the cosmos. The search for extraterrestrial life is a deeply human endeavor, driven by our innate curiosity and desire to explore the unknown. When scientists talk about searching for life, they often mean microbial life first. Simple single-celled organisms are thought to be more likely to arise and survive than complex, intelligent civilizations. On Earth, microbial life dominated our planet for billions of years before complex life evolved. So, finding alien microbes on another planet or moon would still be an incredible discovery. It would suggest that the universe might be teeming with life, even if complex life is rare. Of course, the dream of finding intelligent aliens, beings we could communicate with, remains a powerful motivator. Where might we look for this life? Within our own solar system, some promising candidates include Mars, which may have had liquid water in its past. Jupiter's moon. Europa and Saturn's moon Enceladus are thought to have subsurface oceans of liquid water, potentially harboring life. Beyond our solar system, the focus is on exoplanets, especially those in the habitable zones of their stars. Scientists are particularly interested in Earth-like rocky planets where conditions might be similar to our own. The sheer number of exoplanets means there are many potential abodes for life. To find life on distant exoplanets, scientists search for biosignatures. These are signs or clues in a planet's atmosphere that could indicate the presence of biological processes. For example, an atmosphere rich in oxygen, like Earth's, could be a strong biosignature, as oxygen is highly reactive and needs to be constantly replenished by life, like plants. Methane, in combination with oxygen, could also be a sign. The challenge is that some geological processes can also produce these gases, so detecting biosignatures will require careful observation and interpretation with powerful future telescopes. Section 7. Estimating the unknown, the Drake equation explained. In 1961, astronomer Frank Drake developed an equation to help think about the search for extraterrestrial intelligence. This is known as the Drake equation. It is not meant to give a precise answer. Instead, it is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. It provides a framework for considering the different factors that might influence the likelihood of finding such civilizations. It helps us organize our thoughts and identify what we need to learn more about. It is a way to quantify our ignorance and our hope. The Drake equation has several terms or factors multiplied together. The first term is the average rate of star formation in our galaxy. Then comes the fraction of those stars that have planets. Next is the average number of planets that can potentially support life per star that has planets. Then, the fraction of those planets that actually go on to develop life. After that, the fraction of planets with life that develop intelligent life. Then, the fraction of civilizations that develop technology that releases detectable signs of their existence into space. Finally, the length of time such civilizations release detectable signals. The fascinating thing about the Drake equation is how much uncertainty there is in most of its terms. For some factors like the rate of star formation and the fraction of stars with planets, our scientific knowledge has improved greatly in recent decades. We now know that planets are very common. However, for other factors, especially those related to the emergence of life, intelligence, and the longevity of civilizations, we are still largely guessing. These terms involve biology, sociology, and even philosophy. The final number you get from the equation can vary wildly depending on the values you choose for these uncertain terms. So, the Drake equation is not really about getting a definitive number of alien civilizations. Its real value lies in its ability to stimulate discussion and guide research. It highlights the specific questions we need to answer to better understand our chances of finding company in the cosmos. Are habitable planets common? Is the origin of life a rare event or a common occurrence given the right conditions? Do intelligent civilizations typically last for a long time, or do they quickly disappear? The Drake equation encourages us to explore these profound questions, pushing the boundaries of science and imagination. Section 8. The Eerie Silence, Confronting the Fermi Paradox. The Fermi Paradox is named after physicist Enrico Fermi. In 1950, during a lunch discussion about the possibility of alien life, Fermi famously asked, "Where is everybody?" This simple question captures the essence of the paradox. If the universe is so vast and if there are potentially many habitable planets and civilizations, as suggested by optimistic interpretations of the Drake equation, then why have we not detected any clear signs of extraterrestrial intelligence? Why is the cosmos so seemingly silent? This discrepancy between high estimates of alien existence and the lack of observational evidence is the core of the Fermi paradox. The paradox arises from a few key assumptions. First, that life is not unique to Earth and can arise elsewhere. Second, that intelligent life can develop technology capable of interstellar communication or travel. Third, that the universe is very old, giving civilizations plenty of time to develop and spread. If these assumptions are true, then we might expect the galaxy to be teeming with advanced civilizations. Yet despite decades of searching through projects like SETI, the search for extraterrestrial intelligence, we have found no confirmed signals. This great silence is both puzzling and a little unsettling. There are many proposed solutions to the Fermi paradox. Perhaps life, especially intelligent life, is extremely rare. Maybe the conditions needed for life to arise are much more specific than we think. Another possibility is that intelligent civilizations tend to destroy themselves before they can become interstellar. This could be through war, environmental collapse, or misuse of technology. Some suggest that advanced civilizations might exist but are not interested in communicating with us, or they are too alien for us to recognize their signals, or perhaps they are deliberately hiding their presence from younger civilizations like ours. One intriguing concept related to the Fermi paradox is the Great Filter. This idea suggests there is some barrier or challenge that is extremely difficult for life to overcome. This filter could be anything from the initial leap from non-life to life, to the development of multicellular organisms' intelligence or the ability to survive long-term technological advancement. If the Great Filter is behind us, it means that life, or intelligent life, is exceptionally rare, and humanity might be one of the few, or only civilizations to have passed it. If the Great Filter lies ahead of us, it could be a warning about challenges our own civilization might face in the future. Section 9. Our Future Journey. Charting a Course to the Stars. Humanity has an innate drive to explore, to venture into the unknown. From the earliest migrations across continents to voyages across oceans, we have always sought new horizons. Space exploration is the natural continuation of this ancient quest. The cosmos presents the ultimate frontier, filled with mysteries waiting to be unraveled and worlds waiting to be discovered. Our journey to the stars is driven by our curiosity, our desire for knowledge, and perhaps our hope of finding others out there. This quest not only expands our understanding of the universe, but also of ourselves. Our efforts to explore space and search for life are constantly advancing. Powerful new telescopes like the James Webb Space Telescope are peering deeper into the cosmos than ever before. They are capable of studying the atmospheres of exoplanets, searching for those crucial biosignatures. Missions are being planned to explore potentially habitable moons in our own solar system more closely, like Europa and Enceladus. Looking further ahead, scientists and engineers dream of sending interstellar probes to nearby star systems. These are ambitious long-term goals that will require new technologies and sustained commitment across generations. Interstellar travel, reaching other star systems, presents enormous challenges. The distances involved are almost beyond comprehension. Even the nearest star system, Alpha Centauri, is over 4 light-years away. With current technology, it would take tens of thousands of years to reach it. We need breakthroughs in propulsion systems, perhaps fusion rockets, solar sails, or even more exotic concepts. Then there are the challenges of protecting spacecraft and astronauts from radiation, and the psychological effects of long-duration space travel. It is a monumental undertaking, but history shows that humanity is capable of achieving extraordinary things. Ultimately, the search for life beyond Earth, and our broader exploration of the cosmos, is a journey of discovery. Whether we find simple microbes on Mars, complex ecosystems on an exoplanet, or even signals from an advanced civilization, any discovery would be transformative. And even if we find that we are alone, that too would be a profound realization, emphasizing the preciousness of life on Earth. The universe is vast and full of wonders. It beckons us to explore, to learn, and to grow. The future of cosmic exploration is our future, a path leading us towards a deeper understanding of our place in the grand cosmic tapestry.